with selenium. Hydrothermal pyrites even slower by an order of magnitude. So somewhere between 10 and 100 times faster, depending on what benchmark you're using for pyrite oxidation, seems to be what's happening here. So it's a lot faster. There's nothing to neutralize it though, so it just, once it turns into selenate, it just takes off into the environment. Field leaching may well be slower than we're seeing here. Who knows, it's all a matter of configuration. So, and there also isn't that much selenium to start with. So typical pyrite sulfur concentration might be 5%, and here we're looking at 0.0005%, or 5 micrograms per, milligrams per kilogram. So it's a lot less, 10 by factor of almost 10 to the 4th power, less selenium in the, even the enriched material than there is in typical AMD kind of rock. This is why selenite has a lower atomic molecular radius as a consequence, or ionic radius, so it tends to stick to ferrohydrite, whereas selenate is more hydrated, weaker bond between nucleus and surface. And so what do you do with it? So now we can isolate it. We found that 95% or more of the selenium occurs within a foot or so of the coal. So that can actually be mined separately, isolated. Well, so what? So how do you take that and make something safe out of it? You can put a plastic cap over it, which is extraordinarily expensive, and plastic caps have their shortcomings. The coal industry is accustomed to putting stuff in cells and segregating it, like this black shell. This is an AMD control cell. They're putting lime in it right now. But once you've got that idea, maybe you can put ferrohydrite as a bottom layer on a pile of coal, put pit cleanings on top of that, and put soil or spoil over that to some depth. Well, does that make sense or not? So we're taking our next step out of the laboratory and into the field. These are some plots that are under construction right now at Pt5. This is a view of 30 cells that we have down here under construction. These are 16 by 24 foot boxes, 4 foot deep maximum. So here's one of the cells under construction where we've put a layer of ferrohydrite in, and then we're next piling pit cleanings on top of that. These pit cleanings have about 5 milligrams per kilogram of selenium in them. And then we'll collect all the leachate from all 30 of those tanks, cells, into these tanks here. So we'll be able to measure flow, concentration, loading over a period of time and see if it matches up to what we're seeing in the laboratory. Thank you. Any questions?
You can unmute your phones now.
So at Hobart, you were saying it's what we'll call the fire clays, or the above coal seams where the majority of the selenium is. Currently,
Yes.
Hobart has not been handling that as a toxic material to date.
I think what Hobart's been doing is simply isolating it and then compacting a cap around it.
Okay.
And between you and me, most of the material in, I don't know, caps are caps, but there ain't a lot of clay in that part of the world. So the capping material, I'm sure it's a learning curve, has to be improved or you move to another technology, one or the other, but I'm not convinced that caps really are that effective. There may be another way of hydrologically isolating a pile of bad stuff, but there ain't a lot of clay there to deal with.
I'm just curious about the concentrations from the tribs on the north side of the river versus, say, Connolly and Lukey that are the more recently mined
You're talking about Stanley
watersheds.
Branch and Sugar Tree?
Yeah, have you looked at any of the selenium data from the tribs, and what does that look like in comparison for the older mining stuff, which I think was the 80s, wasn't it? Some of that, or was it 90s?
I don't really know. I would say at least 90s.
And Connolly was 2000 something, right? And Lukey, they weren't done till later, so
I think they're still active mining in Connolly.
that's what I mean. They're still so.
But certainly Stanley Branch is one of the older ones. Actually, Todd has some more recent data on Stanley.
As far as this idea that the selenium leaching is going to slow down, couldn't you look at that by looking at Sugar Tree and Stanley versus?
Maybe, but the problem is they've only been measuring selenium for, what, 5, 6 years now? It's only been an issue, so it's a very short period of time. But it's a good point.
But I mean,
If we
they're
have
the same
data,
concentrations, and one of them was mined 10 or 15 years earlier.
yeah,
Yeah.
that's a good point. We could probably get that data. But I think the concentrations that I've been seeing are in the I don't know, 10 to 15 range. I don't think it's a whole lot different than what we're seeing lower down in the river, just because so much of the flow in the river at that point is coming off, this portion of the Hobbit mine.
There's not a lot of dilution through there, yeah.
No. So that's why it stays pretty much the same value all the way down to the river, down to the reservoir.
I have a question on depth of sampling for selenium.
Yes?
You've gone, I think, 5, so 10 centimeters. Do you have any plans to go further down? Because I'd be interested to find out the extent of selenium occurrence in there.
Well, we went down to a total depth of 20 centimeters.
Okay.
And we don't plan to resurrect that study or redo that. I think the fact that I think at that point you simply look at the total amount of sediment that you have, and it's probably more important than its concentration seems to be fairly consistent. To answer your question, no, we did not see a point where the selenium broke off at depth.
What about the distribution of organic matter in there?
Distribution of organic matter with depth.
Those numbers were about the same as the selenium, so it didn't really tail off either, but we do have a slide here.
Remember, when you ask questions, to say who you are and where you're from. Thank you.
Yeah, mine is both from region.
Dave Cardwell, Region 3.
Oh, hello, David.
Oh, is that all?
Yes,
Okay, I thought it was one of the topics.
I haven't seen you for a while.
Pretty good study.
Thank you. Well, if you look at slide 18, you'll see the total organic carbon really doesn't change very much as you go down through at least the first 20 centimeters.
Oh, yeah, okay.
This is Maggie from EPA Region 3 Wheeling. What about manganese? Did you look at manganese in the sediment at all? I'm wondering.
No, we did not. Now, once you get into the sediment geochemically, there are a number of things that can happen. One, you can start reducing selenium down to either organics, which may or may not be volatile. They may be biologically active, and so you might be losing some out through the water column. You might get into the biologically active portion, methanose, cellulose, cysteine, and some of the other compounds are more or less biologically active, so they could then get into the food chain. Or you might reduce it all the way to either a selenide, precipitating out with a metal like manganese or iron, or you might be generating elemental selenium. And certainly the reduction is probably strong enough there to get all the way down to elemental selenium.
I mean, it's probably a dumb question, but just as black as it is, I wonder how much of that might be due to manganese rather than organic matter. You think that's all organic?
I mean, the black
The
itself.
color itself, yeah.
I know from my soils work out west, I was always astonished how little organic matter it took to turn
Okay.
something perfectly black. A percent is considered pretty high.
Okay.